Okay, so again, my name is Oudega. Unfortunately, my co-presenters couldn't be here today, so I will present their slides as well, hopefully do a good job. So you've already heard about PFAS and how toxic they are. I would like to focus more on the persistent and mobile aspect of them right now. So we have four major point source categories, which are industry, wastewater treatment plants, solid waste, such as landfills, and firefighting foam. Eventually, PFAS from these sources will most likely end up in rivers. So in this study, we are focusing on the pathway from river to drinking water through the riverbank. And riverbank filtration is a cost-effective method to reduce unwanted waterborne agents such as bacteria, but the effectiveness of PFAS is not well known. So I have two parts. One is about the monitoring study that we did, and one is about the modeling. So first, the monitoring, where we asked ourselves which PFAS compounds are present at riverbank filtration sites in the Danube catchments. What are their concentrations, and to what extent are they filtered or retained in these filtration systems? So we did monitoring in Vienna and Budapest, one transect in Vienna and two in Budapest. We had bi-monthly sampling campaigns for a period a little over 1 year, and we measured 32 PFAS in each sample. So I'll focus on the Budapest transect right now. They are located on a Danube island north of the city, which is used for drinking water abstraction. And they both have a pumping well and several monitoring wells, which were all sampled. And the aim here was, again, to study the removal by bank filtration in a force gradient flow field without any clogging of the riverbed and at varying river stages. So here are the results. Can we remove this bar? Okay, yeah. So on the left in orange is the value at the Danube. And then, to the right, we have the values in groundwater. And so from the 32 PFAS that we tried to measure, we found around 9 or 10. The concentrations are quite low. So in the area of a few nanograms per liter. Some are just above the limit of quantification, which was about 1 nanogram per liter. And also the legal limit, which is the sum of 20 PFAS, shouldn't be higher than 100 nanogram per liter, was never breached. We did find minimal sorption during riverbank filtration, and if we saw a reduction in concentration, it was not very consequent, so it was very dependent on location and substance. We also saw elevated concentrations of PFAS inland, so behind the pumping well, especially in PFOA and PFOS, which is surprising because these substances have been banned for a number of years already. So we thought they must come from local sources. Maybe there was a wildfire, or there's some agricultural input, construction sites on the island, for example. So we wanted to look at the groundwater flow direction and the water age to see where this water comes from and how old it is. And for that, we are using the modeling. So besides answering these questions, we're also looking at scenario analysis, where we wanted to look at the impact of future changes on PFAS groundwater concentrations, changes such as climate change, accidental spills, which tend to happen from time to time, unfortunately, and also water pollution control measures. So we have a model train with different scale models, from catchment scale to very small scale. Here we are focusing on the smallest scale, so at the end of the model train, where we have two different models for bank filtration. We have a regional model built by Deltares, which is looking at these water flow pathways and water age. This is the whole Budapest island. And at TU Vienne, we are doing two cutout models for the two sites with a higher resolution, which allows for more precision. And we can also validate our column test results on a field scale study. Then there's also a generic model built by KWB, which is used to predict PFAS groundwater concentrations for a wide range of situations. And again, we can use all these models to calculate scenarios to understand the impact of future changes. So here you see the hydrogeology of the Danube Island. This is based on the interpolation of pore profile data with 4 different lithologies. It has 43 layers of 0.5 meter thickness and 50 by 50 horizontal resolution. Here you see a cross section. So it's mostly sand and gravel. And on both sides of the island, we have the Danube. So here are the first results from the regional model by Deltares. So they are using streamlines, which are calculated by ModFlow using forward particle tracking. This results in a travel time distribution, and applied to this is an advection dispersion reaction equation. And you can see here the results, and also already there are some limitations you can see from this, especially from the scale. So the model thinks that the river boundary is down there because it has a 50 by 50 resolution. But you can see that the time it takes for the particles to reach the well is very fast from the riverbank. So it's also only a few weeks. But from the other side of the well, it can take years. And this is also a solution to our problem of these elevated concentrations inland. So it's possible that there was maybe some agricultural input years ago. These PFAS then come into the unsaturated zone. It can take a lot of time to reach the groundwater level, and then it can take multiple years to reach the well. So the cutout models that we are making, the boundary conditions are here taken from the regional model, and the resolution is much smaller, so we can also model everything in more detail. The wells, for example, have 5 horizontal well shafts. And the goal is to see here if concentrations in the wells are accurately modeled. And the secondary goal is to compare these 2 models to see which is better for which use case, and if you really need such a elaborate and high resolution model. These are the first results. So we have here concentrations for 3 substances of the monitoring period. And in blue, we have the measured concentrations, and in red, the simulated concentrations. So the model works quite well. We're using here one-side kinetic model for sorption, and the parameter values are taken from the column tests that I presented before. So there are some discrepancies. For example, in the monitoring well number 3, we have a much lower simulated concentration than measured. And this is probably because we have a too short warm-up time. As I showed, the water takes a long time to reach this well. And I think we did 4 years here, so we might need to step that up. Then a little bit about the scenario analysis. So we want to predict the impact of future changes on PFAS groundwater concentrations using the model train that I talked about before. And these concentrations will then be compared to health risk targets. So we have a reference period. And then we have 3 scenarios. The first scenario is business as usual. So industry will just continue pumping PFAS into the environment. We will have climate change on top of that, which will, for example, increase low flow events, which can affect concentrations. Then we have scenario 2, which is an accidental spill. And the third scenario will be water management measures, for example, granular activated carbon or groundwater remediation. And in the end, we will come up with a kind of risk table like this, which is again also based on this PFOA equivalent concentrations. Then some few words about the generic bank filtration model by KWB. So this is a simple and easy to use assessment model for PMTs, not only PFAS, also other persistent mobile toxins. It's analytical calculation, and site-specific conditions can be set by the user, such as travel time or soil type. And the code is freely available on GitHub for anyone who wants to try it. And the results look like this. So we have breakthrough curves based on the half-life of the PMT and the log KOC, so the partition coefficient between water and octanol. And we can also create these kind of attenuation heat maps. So to conclude, PFAS concentrations in river and groundwater are below the current limit according to the EU Drinking Water Directive, but sorption during bank filtration seems to be very low. So if the emissions go up, or if the guidelines are becoming more strict, we need to look at different methods to reduce our environmental concentrations. The riverbank filtration models have been validated to the monitoring data. I must say really calibrated, because we had too few measurements for that. But we are ready to start the scenarios, which will map future human exposure risks using these kind of model trains. So for example, for climate change, we will use an emission model combined with the catchment scale model, which will then feed into the regional and cutout bank filtration models. And similar things will be done for the accidental spill situation and for the water pollution control. So thank you for your attention.
Thank you, Thomas. If you have any questions. Perhaps one. Can you give some details about some, let's say, validity of the model in the unsaturated zone?
We have no,
depending on the, on some above or under 5 milligrams per liter.
We have no. The model is only concerned about saturated zone.
Only saturated zone.
We've taken out the unsaturated zone. We're only looking at the transport from river water directly into groundwater.
Okay. And you work only with KD, KOC, and so on, not with interfacial action? Or...
No, we thought about adding more complicated interactions, but because we have so little data, it's hard to really calibrate. If we introduce more parameters, then who knows what kind of values we should put for that. So we try to keep it as simple as possible so that we can use the column test results.
Okay, that means that you take the column test parameter as general, and you put it in your mode flow, and you use it then after in your model. Only the data, general data that you get in the one-day column.
Yeah.
Okay.